So last time we introduced the Debye model, which is a reasonable approximation to account for the phonon dispersion and density of states. And the underlying assumption is the acoustic phonon branch that dominates at low momentum transfer. Okay, so this linear dispersion of phonon at low energy and low momentum transfer limit is the starting point of the Debye approximation. And he took this assumption, linear dispersion, and assumed that the density of states shows a cutoff at a higher energy or frequency, which we call this Debye frequency, omega d. And it's usually inversely proportional to your lattice constant, because that's the natural cutoff in real space, and the inverse of that natural cutoff is natural frequency cutoff. And so from zero energy or frequency up to the Debye frequency, you get this density of states profile that is contributed from the phonon. And this is the Debye approximation, where the density of states in the three-dimensional lattice and with the linear dispersion is actually proportional to the quadratic of the omega, meaning this omega squared, with a proper coefficient. And the proper coefficient, which we call this capital A here, could be fixed from this normalization condition, that total number of phonon modes is actually 3 times lattice size, 3n, which is the integral over the density of states from 0 to Debye frequency. Okay, so it's more convenient to define a Debye temperature, theta, which is the effective temperature coming from the Debye energy. Okay, h bar omega d is a Debye energy, which is leading to effective temperature, which we call the Debye temperature theta, and the Debye energy is in terms of Kb times Debye temperature. So in terms of the Debye temperature, the density of states is given by this form with a proper normalization, prefactor 9 times capital N and h bar square over Kb theta, everything cubic times omega square. So I assign this Debye density of states to you as a homework exercise, that you are able to derive the prefactor in front of the omega square, which comes naturally from all these assumptions and approximations here. All right? Okay? It's a simple exercise. Good. And one remark, that the Debye temperature, which defines the relevant temperature range that the phonon contributes to the thermodynamics. And usually in solid-state systems, theta, or Debye temperature, is actually ranged from, say, room temperature 300 Kelvin up to 1,000 Kelvin. Okay, so which is the temperature cutoff, below which you got a phonon contributions, and above the Debye frequency or Debye temperature, the phonon disappear. Good. So it's a really high temperature limit which will cut off the phonon contributions. So let us just plug in this definition and express this density of states in terms of the Debye temperature and omega squared dispersion of this density of states. And you plug in the density of states in terms of this Debye temperature, and you defined a new dimensionless quantity x, which is the ratio between h bar omega energy and to the thermal energy kBt. So h bar omega divided by kBt is your new dimensionless quantity x, and you could change your variables from omega to x. Okay, but change of variables, and you could do that change of variables pretty easily, and at the end of the day you'll get the dimensionless integration dx and all these prefactors. coming from this transient variables and multiply all this complicated, the thermal factor, including this x to the power of the fourth, e to the x, and e to the x minus 1 with a square in the denominator. Okay, so this is omega square, another omega square, so omega fourth, and omega is x, so this is x fourth, and e to the x minus 1 square. Okay, so everything just fits, and this prefactor is nothing but the omega over there. Is that clear? Okay, so it's a straightforward just substitution, but we are interested in, remember, the solid state physics focus only the low temperature and low energy excitations. So the temperature range that we are interested in should be much lower than the Debye temperature. Okay, so the Debye temperature is how much? Is 300 Kelvin room temperature. So at room temperature, quantum mechanics does not play any role. Okay, only the classical thermodynamics. So of course we don't want the temperature to be that high, so we should restrict our temperature to much lower than the Debye temperature. So if the temperature is much lower than the Debye temperature, this x, say the upper bound of this integral is actually Debye frequency theta divided by t. So if t is actually much lower than theta, the upper cutoff, then this upper cutoff effectively goes to infinity. So in that limit, in the low temperature limit, the upper bound is actually infinity. So you get very simple integration, not simple, but manageable integration over x, where x runs from 0 to infinity. And this complicated object here could be done either analytically or numerically. So you can check the integration table, and this is nothing but a number. Okay? Because x is dimensionless quantity. Okay? So everything that is dimension 4 is hidden here, right? So it's temperature over Debye temperature. Okay? So you can see very clearly that the other factors are temperature independent. So let's just collect everything. So this number is related to this number here, 234 times kb. And you collect all this, temperature dependence factor, which is T over theta to the power of 3, which is here. So this is the final answer of a specific heat contributed from the phonon and taking the low temperature limit. So you can see that the CV is actually cubic in temperature, right? T to the power of 3. You can also evaluate this integral in a high temperature limit. Say this T is actually approaching to theta, right? So, and you could also evaluate this integral, and this leads to a constant specific heat, which is 3 times n times kb. And this is, if you remember your high school chemistry or physics, and this is nothing but the classical specific heat for a molecule, right? So we could actually reproduce the high temperature limit of specific heat and also the specific heat. Remember on the Hartree-Fock section, so we try to evaluate the specific heat of a weakly or non-interacting electron gas, and this specific heat is actually proportional to linearly temperature. And with the prefactor gamma, and gamma here is called specific heat coefficient. And this gamma is actually proportional to the density of states at Fermi level. Remember that. Okay? But here, in addition to so-called electronic or fermionic contributions to the specific heat, we have a bosonic contribution to a specific heat. And phonon is the example of a boson, right? So at low temperatures, we get these two contributions to the specific heat. One comes from the electronic part, another from phonon. Okay? And you know that the phonon contributes to the specific heat to the T to the cube with a prefactor B, which is combination of all those prefactors. And usually, the solid-state physicists, when they measure the specific heat, they usually take the ratio of CV to T, and you get the constant gamma plus T squared behavior. And you could collect your data, and you make a plot of this CV over T versus temperature squared. You get a perfect straight line. Okay, so this is not a theory. This is experimental data. So experimentally, you can measure many different solid-state materials, their specific heat coefficient, and this gamma coefficient, the zero temperature limit is actually the constant intercept, but at finite temperatures, it goes like a T squared. And so if you plot this CV over T versus T squared, you get a straight line. The slope is nothing but the prefactor B. So, by measuring this CV over T, you can fix both the gamma and the B. And you could also very clearly separate these two contributions. And if you look at this electronic contributions, gamma coefficient, this intercept, the value of the intercept tells you the density of states of your electrons at the Fermi surface. Okay? But if you look at these phonon contributions, you simply just can calculate slope of that straight line, and this slope B tells you all this prefactors, say Debye temperature and so on. Okay, so this is really what happens in many materials at finite temperatures when you study their thermodynamics. So you should remember this plot in your mind, and if you're experimentalist, and you could check whether this result is correct by measuring their specific heat. Okay, and you should always see this plot. Great. So finally, let's look at this from the experimental side, how we could determine this dispersion of phonons, namely this, say, omega as function of momentum transfer, this acoustic or optical phonon branches, and how are these features determined experimentally. Okay, so to determine this dispersion, we should perform the neutron diffraction experiments, where you send in a neutron beam, and you hit the target, and this neutron will be scattered by all these atoms and and phonons, and they could absorb or emit the phonon energies, and it gets scattered out. And this scattering is called inelastic scattering, which means that you get some energy loss. And this loss of energy comes from exactly the phonon absorption or dissipation. And you can measure the outgoing, say, neutron momentum, also neutron frequency or energy, and then you could determine the omega as a function of momentum. So the reason why process is inelastic is because we can absorb or emit one phonon or multiple phonons. And we could take advantage of this momentum conservation, and this tells us that this K plus reciprocal lattice vector G is going to be K prime plus minus a phonon momentum Q. Right? So you could either absorb or emit a phonon, but you could conserve the momentum. And the reciprocal lattice is here is because you could take advantage of the crystal momentum and then establish this momentum conservation. And this plus refers to the emission, and minus absorption of a phonon. And number two, energy conservation. So the incoming and kinetic energy is given by the kinetic energy of a neutron beam, and outgoing is the kinetic energy of an outgoing neutron plus or minus the phonon energy. Okay, so this process is actually dominating, this leading contributions to the inelastic neutron scattering. So you could easily solve this two conservation laws, and then you get omega as a function of a q. That's the way to experimentally determine this phonon dispersion. Of course, this omega is actually the phonon frequency here, and the phonon frequency is actually related to this omega prime by again this momentum and energy conservation. So we are about to finish this phonon section, but before we end this chapter, we should discuss the Anharmonic contributions to the phonon energy. And as I mentioned, so far we only care about this harmonic contributions to the phonon energy, and that is because the three phonon approximations could actually tell you many things about thermodynamics, for example the specific heat. However, to really reach this thermal equilibrium and also to account for this thermal expansion, this harmonic term is not sufficient anymore. Okay, so we need to go higher order than the harmonic second order approximations. Therefore, we need to go to the third order approximation or third order term in the potential profile, and that cubic term, and usually we call this Anharmonic term, H3. So let's take a short break, and when we come back we will study the third order expansion of this potential term and how this term is going to help us to reach the thermal equilibrium. So by the way, you could very easily check all these equations in all these textbooks, even this Kittel's Ashker-Mermian and Kittel's second book and Flansburg is everywhere. So it's a pretty standard solid state. But these results can be better understood if we really apply the second quantization and we second quantized this harmonic, say, the lattice vibration, and we define the phonon energy. So things becomes straightforward only if we apply the second quantization rules. Okay, so let's look at the limitation of this harmonic approximation. So in short, we only consider the free phonons in a harmonic approximation, meaning remember the Hamiltonian of the phonons consists of kinetic energy and potential energy, right? And we could decouple all these normal modes for this phonon vibration, and so all these phonons are decoupled. Okay, this normal mode vibrations are all decoupled, so they don't talk to each other. So there is no phonon-phonon interactions. Okay, so the phonons are really free phonons. Okay, and therefore there's no way that the phonon will decay. Phonon energy will not decay if we restrict ourselves to the harmonic potential, and which means that there's no way that we could explain these thermal expansions. And of course there's no collisions between phonons because phonon cannot interact with another phonon, and at high temperatures the CV is always this constant. And more importantly, if we don't introduce the phonon-phonon interactions, it is not possible to reach the thermal equilibrium. And this is really a serious consequence which we don't want to occur, because we know that for this many body systems we can always reach the thermal equilibrium. For example, if we just combine two objects, one is at high temperature, another is at low temperatures, and we know that there's some kind of a thermal, say, exchange of these particles between the high energies and low energies. So after, if you wait some time, they will actually reach a thermal equilibrium, namely the object with the high energies will go to the cold end, but the other cold particles will actually cross the border to the hot end. So at the end of the day, you could reach a single temperature if they mix up. But to reach the thermal equilibrium, you cannot do that within just a harmonic potential, meaning we really need phonon interactions. So we will explain to you why this is the case, that we really need a phonon-phonon interaction to really reach the thermal equilibrium. But in any case, we do need to go higher order than harmonic potential. So the lowest order that we could expand beyond the harmonic approximation, the third order term. So higher order than harmonic term, say third order term, is necessary. So let's just define this Anharmonic term at third order. Of course, this comes from our Taylor expansion. Remember this potential that leads to the phonon vibration could be Taylor expanded up to, say, second order, which is a harmonic term. But at third order, it should look like this a very complicated object where you have the three displacement vector multiplied together, and this matrix element is actually the third order derivative. Great. So you could make a plot of this potential filled by the ions, and can compare this harmonic and with and without the third order contributions. So there's just some shift of your minima point from some place to another if you include the third order Anharmonic term. But other than that, it looks qualitatively very similar to this harmonic potential, because the third order term cannot modify too much of your potential, since this is a very higher order contributions. But we could also apply the trick that we did before, namely we could Fourier transform this displacement to the momentum space, and we can perform the Fourier transformations and then diagonalize this matrix and so on and so forth. So the H3, after Fourier transformation, take this a messy form, Q dot L plus Q prime dot L prime plus Q. Okay, so we could perform similar tricks as before. We could manipulate those Fourier coefficients, these exponential factors, and we could rearrange and redefine all these dummy variables. So let me write it here. Great. So you could manipulate those exponential factors, and then you could verify that this is actually the same as that thing. Okay? So you could intentionally just add all these 3Q vectors here and dot the L, but then the price to pay that you need to subtract the term that you added actually. Okay? So then you could verify that this exponential factor is the same as this times this. And then you could define this capital R prime and capital R double prime, and this is R prime, this is R double prime. So then you get the same factor, but instead of summing over L prime and L double prime, you could sum over capital R prime and capital R double prime. This is given by the prefactor, the Q prime Q double prime I J of K. Yeah. So this is the Fourier transform of this matrix element, and so let me just explicitly write it down. Okay, so in Fourier's transformed expressions for H3, and this is the final results for this H3 in momentum space. And remember that we could take advantage of this identity involving this reciprocal lattice vector. So if you sum over L from 1 to the left side n, and inside the summation is e to the iq dot L, and this quantity gives you sum over 1 from L equals to 1 to n, which gives you the final answer with n, capital N, if Q is actually the reciprocal lattice vector G, and this gives you 0 if the Q is not the reciprocal lattice vector G. Okay, so this identity has been used many times in the past, so you could take advantage of such a generalized delta function. So we could call this generalized delta function n times sum over G delta G and Q, which is n times delta of Q. And this is called generalized delta function. With the help of this generalized delta function and the Fourier transform of the H3, you could very easily write down this, the H3. So let's take a short break. When we come back, I will write down the final expression for H3 after all these complicated Fourier transformations. So I assume that you could follow this Fourier transformation because they are simply just extended from our earlier procedures. Okay, so let's take a short break. So I suppose that you're more familiar with the second quantized fields and this calculations. So the remaining part of the semester involves the applications of all this Hamiltonian expressed in terms of the second quantized fields. For example, we will discuss electron-phonon coupling once we finish the phonon, and then we could start the BCS theory of superconductivity, and then we can go back to this, the spin waves, magnetic properties of solids, and Maganon, and so on. So let me just write down this final expression. Okay, so at the end of the day, we only collect this third-order term in this displacement vector in Fourier space, which is the product of the three displacement vectors. So we know very well that this both y and p, this displacement and momentum, could be second quantized in terms of linear combinations of a phonon creation and destruction operator. And we get this lattice delta function, which is the condition that we need to satisfy in order to have the finite contributions, which means that this q plus q prime plus q double prime should be 0. And by the similar manner that we define this free phonon, we could also define this Anharmonic term, and then this is nothing but a cubic term in the AOA dagger or BOB dagger. Okay, so at the end of the day, you know very well that each of this y here is actually proportional to B dagger plus B, right? Okay, so that's from a simple harmonic oscillator. When we second quantize simple harmonic oscillator, you get the replacement of the y displacement vector by a B plus B dagger, where B is the destruction and B dagger is the creation of the phonon. So when we create a boson of the phonon, remember that you need to actually reverse the plus, add the minus sign in front of this vector q here. Also, we have a polarization vector, everything the same. So the only thing difference, or make this slightly complicated, is the product of the three B plus B dagger. This is what we call the phonon interaction, because now you could collect all these different terms. You got three B daggers. You got three B's. And you also get two B dagger and one B, or two B, one B dagger. So clearly, those terms are phonon-phonon interaction term. Okay, meaning you could, out of a vacuum, you could create both three phonons. And you could also annihilate the three phonons, and the three phonons disappear and they merge into the vacuum. Of course, you could destroy the phonon but then you create another 2. So that's B dagger, B dagger, B. And you could do the reverse, that you could merge 2 phonons into the single phonon. Meaning you destroy 2 phonon, and then you create another phonon. So 2 phonon become 1 phonon. So all these 4 different processes are, in general, the phonon-phonon interactions, because your Hamiltonian H3 is no longer this quadratic form, B dagger B, with the energy. But then this H3 is actually all this complicated phonon-phonon interactions where those terms involve 3 phonon operators. So next week, we will analyze all these 4 different processes and discuss what kind of processes are physically relevant and why are they related to the equilibrium, thermal equilibrium. Okay, so I guess that's enough for today. And please read the corresponding chapters and do your homework. And we don't have class this Wednesday, but we will come back next Monday.